This video includes more examples of integration by parts and a review of how we use the formula. So this is our formula, the integral of u dv equals u times v minus the integral of v du. Again, remember, we're just taking an integral that we have and we're rewriting it in a different form. And our hope is that this form will be easier to evaluate. More specifically, our hope is that that integral over there will be easier to evaluate. In order to use this formula, the first thing we have to do with any integral is choose u to be the function with the simplest derivative. If you've already decided that integration by parts is the way to go, you're going to choose u to be the function with the simplest derivative, and then dv will be everything else, including the dx. Here are some guidelines. If there is a natural log, you're probably going to want u to be natural log of x. If there is an inverse trig function, you want u to be the inverse trig function. If neither of those are part of your integrand, u is usually the polynomial. Now, occasionally there are exceptions to this, but these are just some guidelines. In our class, you're going to see integrals where u is the natural log of x, where u is an inverse trig function, or where u is a polynomial. Those are the three cases we tend to see over and over again. There are some more advanced integration by parts problems in your textbook, but these are the ones that I expect you to know, those three cases. Now, as you're choosing u to be the function with the simplest derivative and dv to be everything else, keep these guidelines in mind. Remember, you also have a couple of constraints. In order to use this formula, you need to be able to compute du. Whatever u is, you need to be able to take its derivative. That's usually not a problem in our class. The most advanced functions that we'll be differentiating require the chain rule. But occasionally you might have something strange like x to the x, where you'd have to do something else to find that derivative. So remember that whatever you choose for u, you need to be able to compute its derivative using your basic rules in the chain rule. You also need to be able to anti-differentiate dv. So whatever dv is, I need to know what its antiderivative is. That's one of the reasons why we use u to be the inverse trig functions when those show up. I don't know the antiderivative of, say, arctan. I don't have that memorized. We know derivatives of inverse trig functions. We talked about those in Calc 1, but we don't know antiderivatives. At least I don't have them memorized off of the top of my head. So I'm not going to put arctan of x here, arctan of x dx, because it would require integration by parts to even find v. So you need to be able to differentiate u, and you need to be able to anti-differentiate v using usually nothing more complicated than a u substitution in your basic rules. Now, after you've chosen u to be the function with the simplest derivative, one of these guys usually, and dv to be everything else, then you need to differentiate u to find du. Don't forget to multiply it by dx. And anti-differentiate dv to find v. One of the reasons why I like this setup is you're going to fill in u and dv, and then it's clear. If you're going down, you're differentiating. If you're going up, you're anti-differentiating. So you're going to find those and then fill in your table. And then you're going to substitute your answers into the formula. So you're going to have an answer here and an answer here. And according to the formula, you get u times v. So you're going to multiply straight across minus the integral of v du. So you're going to have all those pieces. You're going to write that down right here. And then you'll evaluate the final integral and simplify. It's actually pretty easy. It's not too bad once you get the hang of it. Okay, now remember, before all of this, I guess step 0 is, looks like an egg. You need to ask yourself if basic rules or u sub applies. If those apply, use them. If not, then we go to our most advanced technique so far, which is integration by parts. Okay. So let's do an example. Let's say we've got x times sine of 2x, and I'm probably going to use integration by parts. Now first of all, I ask myself, do I have a basic rule for this? And I don't, because I've got a product, and we don't have an antiderivative for product rules, except for this one. Then I would ask myself if u substitution applies. Well, u sub might apply because of the 2x that's inside, but the derivative of 2x is just a 2. And I've got an x dx here, not a 2x dx. And the fact that there's an x, that's a little bit of a problem. The derivative is just a 2, it doesn't have an x in it. So u sub is not going to work. So integration by parts is the way to go. Now remember, everything here needs to be accounted for. U is part of this, and dv is everything else. So I'm going to go through my guidelines. There's no natural log, there's no inverse trig function, and I want u to be the function with the simplest derivative. Derivative of x is just 1. Derivative of sine of 2x is cosine of 2x times an extra 2. It's much more complicated than a 1. So u is going to be x, and dv is everything else. Now I'm going to set up my table. Now I'm going to fill in my table so that I can substitute into the formula in a bit. In order to calculate du, I'm going to differentiate. And then to calculate v, I'm going to anti-differentiate. The derivative of x is just 1. I'm going to multiply by dx to get du. The antiderivative of sine is negative cosine. Since I've got a kx inside, I have to divide by the k when I take the antiderivative. And you should check. Derivative of negative cosine is a negative sign, so it's going to make a positive sign. And the 2 times the 1/2 is going to give you the 1 out front. So that works. So we've identified u and dv. We write down our table. We differentiate u, and we anti-differentiate dv. And now we're going to multiply straight across. That's u times v. And then we're going to subtract the integral of v du. So we substitute into our formula. U times V, that's a -1/2 x cosine of 2x. I decided to simplify as I went this time. You don't have to simplify at first. You can simplify later if you want to. But I just like to pull that polynomial in front or to the right of the coefficient. So I've got u times v minus the integral of v times du. So I'm subtracting the integral of -1/2 cosine of 2x times 1 dx. And subtracting a negative is the same as adding. And I can pull out that constant of 1/2. I'm here now. And my hope is that this integral is simpler than the one we started with. And it is. That was a polynomial, first degree polynomial times a trig function. And this is just a constant times a trig function, or 0th degree polynomial times a trig function. So it is simpler than what we started with. That's a good sign. And I've got a rule for that, so I can finish it. Antiderivative of cosine is sine. If I have a kx inside, I have to divide by the k. Don't forget your plus c. And then we simplify. I'm not going to check, but we could very well check. If I take the derivative of this and simplify, better get that back. Turns out you do. Turns out it works. All right, so that was our first example. Here's another example. First, I don't have a rule for that because it's a product. U sub is not going to work, so I'm going to go to integration by parts. Now remember, you want u to be the function with the simplest derivative, and dv to be everything else. Now polynomials are simple, but this one has a natural log in it, so we're going to use our convention. Anytime there's a natural log in your integrand, you want that to be your u. dv is everything else. So u is natural log of x, and dv is the x squared minus 3x. Don't forget your dx. Now we want to differentiate this. The derivative of natural log of x is 1 over x dx, and the antiderivative of x squared minus 3x, using the power rule, add 1 to the exponent and divide by the new exponent. Bring your constant down. Add 1 to the exponent, divide by the new exponent. We don't need the plus c whenever we do integration by parts. All right, so we're here. We differentiated to get du, and we anti-differentiated to get dv. All right, and we started with u equals natural log of x, because if there is a natural log, that is your u. All right, now according to our formula, we get u times v minus the integral of v du. So I have u times v. I'm going to write the polynomial first. Minus the integral of v times du. All right, looking good. Now, be careful here. I see many students, after they do this, they'll take the antiderivative of this piece and then multiply it by natural log of x, the antiderivative of this piece. Don't do it. There is no product rule for antiderivatives. You've got to simplify this first, or possibly use integration by parts, or use substitution. Remember, this 1 over x is an x to the -1. You can distribute that x to the negative 1 in, or you can think of this x as canceling with one of each of those x's. So let's write that down. Oops. This x reduces with one of those. I'm going to have 1/3 x squared. And this x reduces with one of those, minus 3/2 x. If you're not sure about that, you might do some algebra off to the side and check. Actually, I'm going to do the algebra off to the side just to show you. Just taking each of these guys and dividing it by x. One of those x's is going to cancel. One of those will cancel. So we get this. This is scratch work. It's separate from the line of reasoning over here. If you're doing your work for your professor, if you're doing your work on a test, make sure that this is completely separate. All of this reasoning should be easy to follow for anyone. If you had that in the middle here, it might not be clear what's going on. The way I've written this is equal to this. And now I'll be able to take the antiderivative of this piece and then I'll be done. So I've got 1/3 x cubed minus 3/2 x squared times natural log of x. And then here I'm subtracting, bring the 1/3 down, add 1 to the exponent, divide by the new exponent, bring the 3/2 down, add 1 to the exponent, divide by the new exponent plus c. I'm going to clean up my answer. 1/3 times 1/3 is 1/9. Distribute the negative. This is going to be negative 3/4 times a negative is positive 3/4. And that's our answer. Okay, now let's do one with an inverse trig function. Let's say arc sine of 2x. Now remember, I don't have a rule for arc sine. I don't have an antiderivative rule for arc sine. So basic rules don't work. U substitution, you could do a U sub first and then do integration by parts, but to simplify things, let's go straight to integration by parts. If I do integration by parts here, I need to identify U, I need to identify dv, and whatever I choose for U, I have to be able to take the derivative of, and whatever I choose for dv, I have to take the antiderivative of. We don't have a rule for arc sine of 2x. If we did, we would just write it down and we would be done. So arc sine of 2x can't be my dv. So arc sine of 2x by default has to be my u. And that's fine. You may have forgotten, but we did talk about the derivative of arc sine in Calculus 1. So you've got a derivative rule for that. You're going to be able to take the derivative of that. And if you've forgotten it, that's okay. We can always look it up or refresh. U is the inverse trig function, and dv is everything else. So in this case, dv is just dx. All right. So now we want to differentiate this. And this is where I'd need to review my Calc 1 notes. You might want to recall, go back in your notes and check it out. The derivative with respect to x of arc sine of x is 1 over the square root of 1 minus x squared. Now, if there's something other than an x inside, you got to put that inside and then do the chain rule. And we've got a 2x, so it's a little bit different than that. So the derivative of arc sine of 2x is 1 over the square root of 1 minus my inside function squared. My inside function is 2x times the derivative of the inside. Derivative of the inside is a 2. That can go in the numerator. Don't forget to multiply by dx. Now this is just a Calc 1 reminder. Most of you probably don't need it. But this is arc sine of 2x. That's not a product. That's not arc sine times 2x. I always have to take the arc sine of something. And here we're taking the arc sine of 2x. So the derivative of arc sine of 2x is this by the chain rule. So we differentiated. And then we're going to go up. We're going to anti-differentiate. The antiderivative of 1 is x. According to our formula, the integral of u dv is uv minus the integral of v du. So I've got x times arc sine of 2x minus the integral of v times du. And remember, when you square 2x, you've got to square the 2 and square the x. So that gives us 4x squared there, dx. Now again, you might be very tempted to make that an arc sine and that an x squared over 2. You might want to just integrate both of those separately and multiply them together. That's not how it works. You can't do that. The integral of f times g is not equal to the integral of f times the integral of g. You can't just take the antiderivatives and multiply them. It's not legal. But you can remember that x is itself over 1 and then multiply straight across. And my hope is, after writing it in that new form, you'll see what rule from Calculus 1 we can use in order to evaluate this antiderivative. Do we have a rule for that? It's not an arc sine because of the x. It is a u substitution. Now remember, whenever we are doing a u substitution, whenever we're checking to see if u substitution will work, we're looking for a function nested inside another function. That's probably my u. Since that 1 minus 4x squared is under a radical, that's probably my inside function. Then I take the derivative of that. Derivative of 1 is 0. Derivative of negative 4x squared is negative 8x. Don't forget your dx. And this is going to work as a u sub as long as I've got an x dx up there. And I do, I've got an x dx. So I know this will be successful. I could divide this by 4 to get the negative 2x dx, or I could just divide by negative 8 to get the x dx by itself. This time I think that's what I'm going to do. I try it both ways because I know some students are more comfortable with one way and some students are more comfortable with the other. Either way is fine with me as long as you don't mix variables. There should not be x's and u's in your integral. It's either x's or u's, not both, unless we're in Calc 3. Then we have more than one independent variable, so that's fine. All right, so now I want to write my integral entirely in terms of u. I'm going to pull out the negative 2, and then this x dx can be replaced by negative 1/8 of du because of what we calculated down here. Oops. So I'm going to pull out the negative 1/8 and pull my du off to the right. I've already taken care of the 2, that's gone. And this is a u, but it's under the square root and it's in the denominator. So I'm going to write u under a square root in the denominator. Then I ask myself, do I have a rule for that? Well, not in its current form, but if I rewrite it as u to some power, I'll be able to use the power rule. So we've got x arc sine of 2x. Negative 2 divided by negative 8 is positive 1/4. And then this is a u to the 1/2 power in the denominator. So that's u to the negative 1/2 power times du. All right. So how do we handle this? We're going to add 1 to the exponent. Negative 1/2 plus 1 is 1/2. And then we divide by the new exponent. Dividing by 1/2 is the same as multiplying by 2 over 1. Don't forget your plus c. That simplifies to 1/2. So we get x arc sine of 2x plus 1/2, and that's a square root of u. And of course we want to back substitute. Remember that u was 1 minus 4x squared in this case. All right, and that's our antiderivative. If I take the derivative of this and simplify, I get the original integrand back. You should check it out if you don't believe me. But let's just walk through this inverse trig integration by parts again. So if you have an inverse trig function, that is your u. Write that down. dv is everything else. You want to differentiate using your inverse trig rules. You might want to look up the arctangent and the arcsecant rules, and then anti-differentiate dv. It's often just dx, and then you just get a 1, or the antiderivative of 1 is just x. Be careful there, it's not 0. A lot of people try to differentiate there. The antiderivative of 1 is x. Then multiply uv minus the integral of v to u. Here's another thing to be careful about. Don't integrate this and this separately. Multiply straight across, get this. Then anti-differentiate this piece. With the inverse trig functions, it tends to be a u substitution. U is typically your denominator, or something under a radical for the arctangent problem, or the arcsine problems, or I think arcsecant as well. So you do the u substitution over here, and then you finish it, and that's it. So remember, you've got 3 types of problems in our class for integration by parts. Oh, actually, we haven't done the last type yet. You've got the ones where u is equal to natural log of x. You've got the ones where u is equal to an inverse trig function. And then the last one is where u is a polynomial. Now, I already shown you an example where u is a first degree polynomial. But if u is a polynomial of degree 2 or higher, actually if it's any polynomial, but especially if u is a polynomial of degree 2 or higher, in this case we want to use what's called tabular integration by parts. And I'm going to show you how to do that in the next video.